Okay, thanks for coming. So today we have a Wonwoo Kang, who is a graduate student at UIUC, talk about some cluster.
Thank you. Thank you for the invitation. I think I kind of skipped the talking part, but it's fine. Anyway, so I'm here to give a talk about the Skein relation for punctured surfaces, but don't worry, at least the first half will be more like an introduction to the cluster algebra from surfaces, so feel free. I actually put a lot of examples and a bunch of stuff, so you don't have to worry too much about, oh, I don't know about cluster algebra. Oh, that's fine. Like, I'm gonna give all the introduction, so it's fine. One small thing before I start a presentation. Every teaching in my UIUC, I always get the comment that I speak too fast and too loud. So if you feel like I'm speaking too fast and too loud, always raise up your hand and always let me know. And of course, if you have any questions, feel free to interrupt me at any time. So the presentation will consist of 4 parts. So first, as I mentioned, I will be giving the introduction to the cluster algebra from surfaces. And second, I'll actually give a more general version of it, which is cluster algebra from punctured surfaces. And then the third and fourth will be my results. Third one is basically the title, the Skein relation for punctured surfaces. And fourth one will be the implication. So let's start with the introduction to cluster algebra from surfaces. So let's start with the small notations. So we will pair up the surface with something called a marked point. So what is marked point? Marked point is basically the finite set of points in surfaces. And if the points are inside the interior of S, we call it puncture. And arc in this pair is a non-self-intersecting curve such that the endpoints are in M and disjoint from M and boundary of S except for endpoints, and it doesn't cut out an unpunctured monogon or an unpunctured bigon. So a small example will be this. So if you look at the first example, there's a torus and there's 2 punctures, and because these 2 marked points are in the interior, we can call both of them as punctures. And if you look at the second example, there's a circle and there's 4 points on the boundary. So all of these marked points are on the boundary, so no one is a puncture there. And as I mentioned in the definition of the arc, it shouldn't cut out monogon or bigon. So if you look at the red arcs cut out the bigon. I mean, the bigon will be the polygon with 2 vertices. So the red arcs will not be arcs. The black one will be the only arcs. And
can you copy? So what's the inside the interior? I see.
Exactly, yeah. So inside the marked points, there are punctures and basically non-puncture.
I see. Okay.
So if the marked points are in the interior, then we call it puncture.
So the
arc is basically the curve that where the endpoints of them are on these marked points. And but with a few rules, it shouldn't cut out those. There are some conditions, and of course.
Doesn't cut
Mm-hmm. And of course, there's a reason for it, which I will explain.
So in a sense, you don't want an arc going through only 2 punctures?
Sorry?
So you don't want an arc.
Oh yeah, like you're talking about, so it seems like, are we talking about this?
Puncture.
Yeah, like if they're, like, are you talking about this one or?
That's an arc going through
This is an arc.
puncture, right?
Yeah, this is an arc because it's not cutting out unpunctured monogon. So there is a monogon, but there is a puncture inside it, so this is fine. Yeah.
Oh, that's I see. So punctured means.
Yeah. Punctured means that in the inside, basically inside any of these parts, there should be either puncture or no. But in this case, in the closed part of it, there's a puncture. So this is okay. But if I say something like this and the punctures are out there, there's not.
What if the surface is like sphere and then outside there is no puncture in it?
No, okay. That's a very good point. So in that case, there's a lot of things I have to say about the sphere part, which is I have to say that's a very accurate question. So in the sphere, there are a lot of, let me just jump into the real meaning of it real quick, but even if it's actually in the second, in the next slide. So technically, like as some of you might expect it, the arc is also actually for the triangulation. So if the surface, I mean, like if there's a closed curve where we cannot make any triangulation, well, technically we don't need any. Well, we can't say there's an arc. So the big idea is that arc is for a triangulation, and if we have some kind of specific concept, like, well, I mean, like, so as you can kind of mention, like if you have a sphere and with one puncture, like we don't even have a let's say we can't even define an arc because, well, like any closed curve will actually discussed as the unpunctured monogon, and also for the two puncture also, even if you have these kind of arcs, but as you can see, these cut out the bygone, so we can't say these are the arcs. So technically, you can actually make a pair. Making a pair of SM is also fine, but in terms of making an arc, there's a difference.
So I have a question.
Mhm.
So what do you mean by unpunctured monogon?
So if we have a surface like this, and let's say a puncture like this, if the monogon encloses a puncture, it's fine. This is okay. This is allowed.
Okay.
But this, we can call this an arc. But if we have this and then like this,
Yeah.
then it's no arc because it's cutting out unpunctured monogon.
Why it is called unpunctured?
That's also a very good question.
It stays inside the interior.
Yes, exactly. So in this case, in the interior of this monogon, we don't have any puncture. So
You don't have any puncture.
yeah. So unpunctured means there's no puncture inside the interior.
Okay.
Actually, for me, it's first time to see the word monogon.
Mm-hmm. Oh.
I usually saw one gon, but anyway, I didn't.
I think it depends on the literature because in our field, I think many of them are actually speaking monogon, stating a monogon. It's fine. Anyway, so examples I explained. So as I mentioned,
Can you show the second picture
Yeah,
again?
sure.
So the surface.
surface S is just a disk. So it's like a disk,
Puncture.
and all four of them are points are on the boundary, so there's no puncture.
Oh, I see.
Uh-huh.
So how do you distinguish the interior from the exterior?
That's a good point. That's a very good point. So I know that someone will ask this. So in the short answer, it will be, as I mentioned earlier, all of these arcs are only for the triangulation. So if you actually construct all the triangulation, and if you have a, let's say punctured monogon, and well, let's say something like this, or something like this can happen. Well, and then it's kind of straightforward that this one monogon is this is the only area that is enclosing by this. But I know what your point is. Your point is actually, well, what if there's a closed surface and let's say like there's a 3 puncture, and then like in this case, how can we distinguish which one is punctured or unpunctured? Well, for this case, there's a very, how should I put it? There's a very, very old result in the triangulation part that, no, I should, maybe rather than explaining in this fashion, I think the better way to answer your question is that so there's a way to embed this into the hyperdisk, hyperplane disk, I mean, so like technically Poincaré disk. So if we actually embed this into the Poincaré disk, all of these arcs will actually be not, so all of the monogon, which seeming like a monogon, which because I mean like the endpoints are the same, the endpoints will be differed. So in that case, it's kind of straightforward to see which part of the surface that is in and what I mean by enclosing, because in that case because it's in the disk, and you can actually measure something called the lambda length, and the shorter one is actually going to be the one that is enclosed by it. So that's actually how you kind of determine which part you will say this monogon is enclosing. So that's I will say more like a mathematical way to explain this.
So if let's say you have torus and you have curve, non-separating curves,
Uh-huh.
so like just
Over and over. Okay.
no, you just have one curve.
Oh yeah.
Then you don't have. I mean, this doesn't bound the disk, right?
No,
In this case, is it an arc?
it's an arc. Yes.
Then is it punctured? No.
No.
What is it?
So
Is that punctured or punctured?
So like I mean, if you think about the the covering space of the torus. Well, I know. So you're saying that like in like this, it's like this.
Kind of clear.
Yeah. So yeah, this is allowed. This is okay. This is correct.
So that's.
Because it's well, I mean the part that is let's say enclosing is not a monogon. Well, if you look at the covering space, it's actually a triangle. So.
Oh, so as long as it's not a monogon, where monogon is this disk with the one thing. I see. So
Yeah.
you don't bound any monogon.
Exactly.
Okay.
So everyone's satisfied with the definition of the arc. Okay, but anyway, like I mean, like again, as I mentioned, the arc is for the ingredient of the triangulation. So the ideal triangulation will be basically making a triangulation of some surface. And well, of course, since we are mathematicians, we need to actually make it in a more like a subtle language. So in our language, we call it a maximum collection of pairwise compatible arcs. And the compatible arcs means that they don't cross each other. So for example, in this like the octagon, like you can actually have this kind of one ideal triangulation, one example of this ideal triangulation of the octagon. So and then after you get the triangulation, you actually assign quiver. So what is a quiver? Quiver is that if we have a triangle inside this triangulation, you assign the arrows clockwise. So in this case, if you look at this triangle, you go from 1 to 2 and 2 to 3 and 3 to 1. And of course, in this case, naturally, it should have an arrow from here to 3 to this boundary and this boundary to the 4. However, we will delete all the arrows which endpoints are on the boundary. So technically, we have this, and first step will be assigning all the arrows here, but as I mentioned, I don't want to care about the arrows where the endpoints are on the boundary, so I'm deleting these. So I'm going to only care about this one. So that's why I only have 5 arrows in this triangulation.
How do you decide the orientation, direction of the?
Oh. So inside the triangle, clockwise. Yes.
Clockwise. I see.
Good question. Yeah, good question. So.
What about the 4 to 3? So is it also?
So if you look at this triangle, so like here, so technically I like there should be 3 arrows like this, but as I mentioned, I'm gonna delete the arrows which endpoints are on the boundary. So that is why the only 1 arrow here is survived.
So do you only care about the kind of the outer planar triangulation, or do you also care about the triangulation which involves interior points?
Exactly. So which only involves the arcs technically. So technically, I'm gonna care about the arrows where both of their endpoints are arcs.
No. What I mean is that can you also define quiver for a triangulation which involves interior?
Exactly. Yes, you can.
I see.
You can.
I can.
So and then we actually define something called the exchange matrix of this quiver. So how do we define it? Well, if there's an arrow from I to j, you assign bij as L, I mean if they're the L arrows, and minus L at the bji. So, for example, if you look at the previous one, there's an arrow from 1 to 2. So which means that b12 is going to be 1, and b21 is going to be minus 1. So b12, this one, is going to be 1, b21 is going to be minus 1. And like as some of you have already guessed, this is skew symmetric. So now we gather all the ingredients to define an algebra. Now actually we have to talk about the relation. So why do I talk about the relation? So when we want to define something called the algebra, there's a generator and a relation. So generator part is actually I just explained all of it. Of course, I'll give a detailed explanation how they actually going to be assigned to the generator. But this part is actually about the relation part. So how do we actually talk about the relation? So if we have a diagonal and substitute into the other diagonal inside the quadrilateral, there's a famous theorem, I think like it back into like maybe like ancient Greece, that there's something called a Ptolemy relation. Ptolemy relation is that if there's an quadrilateral that is inscribed by the circle, then you actually, if you actually multiply the length of the diagonals, then you actually get the sum of the two arcs that are actually like looking at each other. So what I'm saying is that A, B, C, B, and this is gamma and this is gamma prime. So gamma length of the gamma and gamma prime multiply the same as AC plus BD. So you basically use that relation to define the relation in this algebra. So let's and then the other thing that we have to see is, okay, we talked about the substituting the diagonal. So then what about what happens in the quiver? So the quiver mutation is that if you switch on if you switch on diagonal in the previous slide, I used the language flip. If you flip the diagonal, then you follow those kind of you follow these steps. So first, if we have I to k to j, then you have a u arrow j. So what does it mean? It means that if I have I to k and k to j, and if I have flipped k here, I am getting a new arrow from I to j. And second, for all arrows incident to the vertex k, reverse the direction. So what does it mean? So in this case, so first setup was this, but I'm reversing all the arrows that are adjacent to k. So these should be this, and this should be this. And third one, remove oriented two cycles. What does it mean? It means that if I have something like this, or oriented two cycles, I'm just going to cancel these out. So in this example, if I have flipped 1, the initial setup was this. And as I mentioned, I'm going to flip this part. Then what does it mean? So there's going to be one arrow from here to here because IKJ logic applies. So there's going to be one arrow from here to here. And then I have to flip these two arrows because it's adjacent to the arc that I'm going to flip. And then if you have look in here, there's a two cycles, so I'm going to remove this. So, and then surprisingly, or maybe not surprisingly, if you look at this, this new quiver corresponds to the new triangulation that we have by flipping a diagonal. So basically, it's more like you're trying to unify the logic of the flip into the quiver mutation. So, and then what happens to the exchange matrix? So exchange matrix, it follows this rule. So it's kind of similar. So if there's an adjacent vector to k, you flip. So that is applied in here. And then for the if there's no other parts that is relevant to k, there's nothing happens. But in this case means that there's an I to k to j. It follows this rule. So like even though it looks kind of like a lot of computational thing, no, it's basically you just get the exchange matrix from the new triangulation that you get, and that follows the previous rule. So it's something special. It's just you're just rewriting the exchange matrix out of this new triangulation and new quiver. Okay, I think I kind of convinced up until here, which is very, very great. So the generalization of this Tolley relation which we saw will be written in this fashion. So the question should be, how can we derive the Tolley relation, which you actually called it as a relation in the algebra, from the exchange matrix and quiver and a whole bunch of stuff? You use this rule. So the rule is, if I flip here, so for example, in this case I flip 1, there's actually a 5 times 5 exchange matrix. You only think about the element, the components in the first column. So how do we actually think about it? You actually get the rows where BIK is positive, and you get the rows where BIK is negative. Then you actually put them you put their absolute value in the power of xi. So for example, in the previous slide, the B is this, and I flipped 1. So if you look at here, the first column, the B21, the second row is minus, and the third one is plus. So that's why, the third, the x3 should have power 1, and x2, which was actually minus 1, have an absolute value, which is minus 1, which is just 1. And then you can actually see that this is actually a Tollman relation with the boundaries understood as 1. So what does it mean? I'm saying that if I have 1 prime in here, this is 2 and this was 3. So technically, I should have said, well, xb times x2 plus xa times x3 is equal to x1 prime. But as I mentioned earlier, I'm not gonna care about the boundaries. Boundaries are also all just gonna be 1. So that's why I get x2 plus x3, and that's why I'm claiming that this is retrieving the Tollman relation. So we're done. You just learned what is cluster algebra. Hooray!
Is there an example that of the matrix which has the absolute value at least 2?
Oh, good question. So in here we're only talking about the cluster algebra of surfaces, so it's kind of hard to imagine. But technically, the cluster algebra of geometric type is actually all from the quiver. So you can actually technically construct the quiver where there's 2 arrows from A to B, and that is possible. So, but in surface also is also applicable, but I don't want to talk about the whole language of the folding and a whole bunch of geometry stuff because I'm not a geometrist. So, so yeah, but good question. Yeah, so they technically numbers other than 1 is also possible. Okay, so let's jump to the definition. The definition is that so these variables I stated will be called as cluster, and B is the exchange matrix. And the C mutation is the mutation that I showed earlier. So B prime, the mutation of the exchange matrix, and the exchange relation that I showed earlier, which is more like a generalization of the Tollman relation. So if you actually collect all the x's possible here, then if you define a ring over Z, then it's called cluster algebra. And in our example, this x, which is a tuple of variables, will be all possible arcs in the surface. So in our example, it's all the diagonals. So it's more like assigning like this. So let me actually state it in a more like a manifold way. So my previous example was 1, 2, 3, 4, 5, and technically the new diagonals should be written as 6, 7, and technically n choose 3. N minus 2 choose 2 or whatever. I forgot. I'm not really good at the combinatorial. So anyway, but the idea is that this another diagonal which is not in this triangulation can be described in the language of the first triangulation. So for example, like 6 here, as I mentioned, x1 times x6 will be x2 plus x3. So, and since we're working on a not a polynomial ring, you can actually state it as x minus 1, x2 plus x3. So this is what I'm trying to assert. So other diagonals, other than the ones in the first initial triangulation, you can express them using the language, using the variables of the initial triangulation. And that is done by the, in geometry language it's Tollman relation, but in my language we call it exchange relation. What a fancy word, right?
So is there like a basis change formula?
My gosh. Okay. That'll appear at the end. So keep that question until the end. I have to say, very good question. That is a very, very good question. Anyway, I'm gonna talk about it anyway. Yeah, in the last part, which is very, very good. Any other question? Okay. So, but we don't want to stop in here because mathematicians love to generalize. So, in the exchange matrix that we stated, is always going to be the square matrix. But another question that they actually derived was that what happens if we add more rows? So we call it extended exchange matrix, and since all the exchange relation depends only on the column, it doesn't really hurt the exchange relation itself. And mathematicians define coefficient variable as the multiplication of the variables that you assign in each column. And principal coefficient is the coefficient that you get when this is identity, which is kind of easy one, right? Because it's all going to be 1. And yk is just going to be u to the k. And so if I say this is u1, u2, u3, u4, if this n times n is an identity, then you can actually kind of imagine that uk is a yk. And then the exchange relation will be actually derived like here. Don't worry if you don't fully get the whole idea, it's totally fine. The only thing that you have to understand is that I'm going to make a generalization of the closed algebra that I actually mentioned using the new variable yk, and I'm only going to use this exchange relation. Other question? Maybe some of you might think that why do we care about the coefficient variable and blah blah blah. Let's talk about it after the clock, because that's actually, there's a very deep fundamental thing behind there. So okay. Oh gosh, okay. Maybe I'm being too energetic. Yeah, okay, so we've done with the introduction. Now let's talk about the closed algebra from punctured surfaces. And naturally you will say, what do you mean? Like, we've been talking about this, right? Actually no. Because the thing I'm assuming in the previous one is that I can flip all the diagonals. However, if you look at this construction, which is also an ideal triangulation, natural question is that, like, can you flip gamma where you can get other ideal triangulation? So some of you might think that, well, if we have this kind of construction, and if you want to flip them here, why can't we say something like this? Well, like, there's an intersection, right? You don't want that. So that's why we want to substitute this monogon into the other picture. So what do you use? So you use something called a notched arc. Notched arc is that basically you substitute this monogon into the arc. Oh, I'm not clicking any of this. Okay, this is totally fine. I'm used to the ad-lib. So you just put a notch on this part to notify that this was actually worked like a monogon. So what happens? So what happens is that if we substitute the monogon into this picture, at least in pictorially, it looks nice, because if we flip this monogon, you get this. And then if we flip the gamma, which was the troublemaker, you can get this. So rather than depicting into this fashion, by substituting the monogon into this fashion, I can draw this with like this. Of course, some of you might think that, okay, this is just like sweeping the whole thing under the rug. Why are we doing this? The big reason is, as I mentioned, we want to flip this gamma, so that the relation that we defined can be applied to every variable. And then, so naturally, we need the new definition for the triangulation. The new definition for the triangulation is called tag triangulation. So now, number one rule is basically the same thing. Like if we remove all the notches, they should be compatible. And the second and third one implies that if they're, well, I mean, like, second and third rule, you think is like, well, what are they talking about? Let me just show you with the picture. So the second rule is that if we remove all the tag, and if they're the same, so if I remove this, they're just going to be the same, right? And the rule says that at least one endpoint should have the same notch. So in this part, both of them are plain. So this is okay. However, if you look at this endpoint, one is notch, one is plain, This one is notch, one is plain, also. So this is incompatible. And the and then the third rule was that even if we remove, after we remove the notch, and if they are not the same but sharing an endpoint, at that endpoint, the tag should be the same. So they should be either both plain or both notch. So this one is fine because in this arc and this arc, both of them are notched. But in this case, one is notch and one is plain. No, So this is how we, well, this is also kind of go natural with the setup that I mentioned earlier in here. So the second rule implies this one, and the third rule implies this part. So since we have the new triangulation, you need a new relation. And the new relation is that if you flip the thing inside a monogon or outside a monogon, you get this this relation. So what does that mean? This means that if I have alpha, beta, rho, gamma, and I feel like this. If I flip rho, this is going to be rho prime, and x rho times x rho prime will be just x alpha plus x beta, but you just add the y in the alpha part. Same for the gamma. If I flip gamma, it's going to be gamma prime here, which is the plane arc. X gamma prime is x alpha plus x beta, but of course you actually put the y's in this alpha part. And some of you might have noticed that, well, this is a different rule from here. Well, yeah, because if I follow this rule, because if you think it this way, this is more like identifying this two arcs into one and making it to the monogon. So if I actually apply this rule and apply the flip in this row part, then technically the relation that you should get is x gamma alpha beta, x gamma x alpha plus x gamma x beta, right? But I don't want two different terms having the same components, having the same variable. I don't want that. So that's why by applying the tagged arc, I can remove this gamma at these both terms and write the relation into this fashion. And then, well, cluster, and you can actually see that cluster algebra from surfaces is in this fashion. So one, cluster variables corresponds to the tagged arcs, and clusters correspond to the tagged triangulation, and the relations corresponds to the flips of arcs. So that is called the cluster algebra from surfaces. So from now on, if you have other talks about the cluster algebra, you can bravely say that I know what is cluster algebra. So natural question for the combinatorialist was that instead of non-iterative way to compute the cluster variable. So what does it mean? It means that, as I mentioned, all the diagonals can be written in the language of the first triangulation. So for example, if I have gamma like this, well, I mean, you can flip this and this and this and this and get this gamma. It's fine. But is there a non-iterative way to directly compute this gamma? And it's, unfortunately for all of us, is already answered. So Greg Musiker, Schiffler, and L'Oreal is actually apply the idea of the snake graph to find a combinatorial formula. And recently, XE and Emin also, XE and Emin, this team, and Vincent Nathan Sibyl, this team also invented something called the poset idea. So yeah, so by applying these ideas, you can directly calculate the cluster variable that corresponds to this gamma using the combinatorial tool. So let's jump into my work, which is the most important one. But before I jump into this thing, any question? So this is all the introduction that I prepared. So any questions?
So the number of variables are always finite. There's a correspondence to AD type.
It does have a correspondence to the AD type, yeah. So in our example is AN, yes.
IA.
Yeah. But okay, never thought about that one. Like so, but I think at least the one that we're working on has the finite generators. But never thought of it as is it even possible to have an infinite one? I'll think about it. But at least the formal definitions, the cluster algebra, and all the cluster algebra that at least I know has the finite number of generators. Any other question? Okay, so let's jump in here. So Skein relation. Skein relation. Well, I mean, like for some of you who know the knot theory and like working on the Jones polynomial, will be very familiar with that. So the Skein relation that I'm going to talk is that if we have an intersection like this, I'm gonna resolve this intersection into this and this, which is clearly a Ptolemy relation, right? Because the Ptolemy relation, I stated that if we have a quadrilateral gamma prime, A, B, C, D, I'm making x gamma prime into sum of AC plus BD, right? Which is this and this. So Skein relation is like that. So natural question is that is this Skein relation only applies in this, let's say, like one flip, or the Skein relation holds in general? So for example, if I have gamma and let's say other one, let's say tau, does the Skein relation also apply in here? Which means that does it also have is the product of these two can be written as the sum of these corresponding two pairs, and many mathematicians have worked on it. So Musiker and Williams explains Skein relation in unpunctured surface. So basically, not the tag triangulation, but just the ideal triangulation using an npath. Npath is the matrix language that explains how you can actually interpret the arcs in the surfaces. And Kanachi and Schiffler also describe this relation using snake calculus. And for punctured surfaces, which is the one that we are interested of, the coefficient-free case, so no y, was discussed by Travis Mandel and Fan Qin, and the team that I mentioned, Pilot Reading Scholl, shows special cases of Skein relation in the principal coefficient case. They're actually called the tidy exchange relation. But our work describes all the Skein relation in the principal coefficient case with explicit formula. And what I mean by explicit formula is really explicit. So it's not something that you have to calculate or do something really crazy. It's quite straightforward. So let me show you the examples. And the cases was written in the Musiker Schiffler Williams paper, and it was described in the 15 cases. However, we got to know that they can be regrouped into 4 categories. So 1 is incompatibility at the puncture, 2 is a transverse crossing, and 3 is self-crossing, and 4 is closed curve. So I'll explain each of them and what they really are. So incompatibility at puncture means that they don't follow the rules that I mentioned about the tag triangulation. So in this case, if you look at the gamma 1p and gamma 2, I mentioned that if they share an endpoint, the tagging should be the same. But in this case, they're not, right? So it's incompatible. So that's what I mean by incompatible at a puncture. And this is the, let's say, general example of incompatibility at a puncture. And how do we get the Skein relation? The rule is, so before I talk about the real final conclusion, 2 rules real quick. So let R denote the set of all arcs from T which gamma 1 and gamma 2 both intersect. So if I have a triangulation like this, and then if gamma 1 is like this and gamma 2 is like this, they two both intersect this one and this one. This one is only intersected by this, and this one is only intersected by this, so they're not into R, but these two will be inside R. And then this, but in our case it should be more like this, but yeah, anyway, the rule is like this. And the second, SW denote the set of all the arcs in T which lie counterclockwise of gamma 1 and clockwise of gamma 2. So what does it mean? It means that if you go counterclockwise from here, I'm swiping here up until here. So I'm just gonna look at arcs that have an endpoint at P where can be swept by gamma 1 when I sweep this counterclockwise up until gamma 2. And in these 2 results, of the 2 pairs that we get is kind of straightforward that one pair actually contains all R and SW, and the other pair doesn't contain any of them. So the one pair that contains them, I'm gonna state it as C plus, and the other pair that contains all the that doesn't contain R and SW, I'm gonna call it a C minus. So for example, in this case, so if you look at here, this is gamma 1, gamma 2. And luckily, there's no arc that intersects both of them, right? Like there's no arc like this. So R is going to be the empty set. However, if I swipe this up until gamma 2, it crosses 1, 2, 3, right? So SW set is going to be sigma 1, sigma 2, and sigma 3. And then the resolution will be written as Oh, and then the C plus will be this one, and the C minus will be this one, because C plus is the one that intersects both R and SW. So C plus intersect 1, 2, 3, and C minus doesn't intersect none of them, so C minus is the one. So the resolution will be written as Cx of C plus plus YR, YSW, XC minus. And what are these? Just the product of the y's that you get from here. And then what is transverse crossing? Transverse crossing is actually this one. So transverse crossing is really the intersection of two arcs, which is just written in fancy language in the up until there. But defining R and SW is basically the same. R will be the arcs that are both intersected by gamma 1 and gamma 2. SW is a little bit tricky, but really basically the same. So basically, we will get the maybe. So let me just. So for example, if I have this and this, I'm gonna have a pair of this pair and this pair. And then what I'm trying to say here is that if endpoint, it depends on the endpoint of this gamma 1 and gamma 2. If they're tagged, we cross it in the counterclockwise. If they're plane, you cross it as a clockwise. You sweep them in the clockwise. And the other ideas are the same. C plus will be the pair of arcs that crosses all arcs in R and SW. C minus is not. Of course, I prepared an example like this here. So let's look at here. So gamma 1, gamma 2 both intersect 5, 6, 7, right? Other arcs, they don't cross. There's no other arcs that both of them crosses. And let's look at their endpoints here. What did I say? Well, I say that, sorry. If it's plane, you sweep them clockwise, right? So if I sweep here, the clockwise up until I cut here, I swept 8. So 8 is included in here. And let's look at here. There's a tag here. What did I say? Tag, counterclockwise. Counterclockwise swept, so 3 and 4 is added. So this is how you define SW and R. And rule is the same. XC is like this, and the x1 times x gamma 1 times x gamma 2 will be written in this fashion. And actually, the closed curve and the self-intersection is basically follows the same rule, so that's why I just deleted those slides. Anyway, the result is you define R and SW in this fashion. R means the arcs that are both intersected by gamma 1 and gamma 2. SW, you basically sweep the endpoints with some rules. Basically counterclockwise when tagged, when not, and clockwise when it's plane. And then the Skein relation will be rewritten in this fashion. I'll briefly give the proof idea. The proof idea is that there's something called the separation formula in the closed algebra.
Sorry, but what is the statement?
Sorry. So the first one is about all the cases except for the self-intersection, and this one is for the self-intersection and closed curve, of course. Yeah. My bad. Good job, because as I mentioned, I speak too fast and too loud. So sometimes there should be someone to interrupt me and stop me and cool me down.
So you are considering any surface.
Exactly.
Any
surface. Any surface. It's torus, well, like Klein bottle, any species, which of course can be triangulated. Of course, there's a lot of details I skipped, I know, but result applies. It doesn't depend on genus or anything, no.
Yeah, that is interesting.
Mm-hmm. So the sketch of the proof is, so in terms of, so in the cluster algebra, there's something called a separation formula. Separation formula means that you can think of x with something called a g vector, and you can think of y with something called an f polynomial. So big idea is that we need to find a bijection of this g vector and f polynomial. So f polynomial part is you have to find basically we use the language of the fence poset. I mean the XE and Emin, like the tool that XE and Emin actually use. So you use the poset language to express the cluster variable, all the variables inside this cluster algebra, and then you find a bijection of the order ideals of this of these posets. So that's the big idea. And G vector part is using something called the minimal trunk, but I'm not going to explain that part. But anyway, the big idea is, as I mentioned earlier, is about weight preserving finding a weight preserving bijection between these set of order ideals. So what am I saying is that so big statement is like x like gamma 3 x gamma 4 plus y x gamma 5 x gamma 6. So it's like there is a set of order ideals inside this poset that is assigned for the gamma 1, and a set of order ideals for this gamma 2, and you first define a product of these, and then you want to find a bijection of these into J of P gamma 3 times J of P gamma 4 union J of P gamma 5 J of P gamma 6. So if you successfully find all of the bijection in each of the categories that I mentioned earlier, then F polynomial part is done. So this is very very classical combinatorial idea. So
what is a fence poset? Is it defined by the
So it's actually just a poset. Poset, but the reason why you put the fence is that the poset to define the cluster variable here. Let me just show you a very brief example. Don't worry, it's not going to take a lot of time. So if I have gamma like this, 1, 2, 3. So how do I assign the poset? So if you look at the intersection, it's like they intersect 1, 2, and 3. And you can see here is that from 1 to 2, the orientation is like this. Then you assign the partial order like this. So 1 is lower than 2. And then from 2 to 3, it's like going down, so it's like this. So the poset that you get from this gamma will be written in here, and we call it fence poset. Any other question? So natural question is, well, I mean, like, okay, it looks fancy. I mean, like, you can find all the Skein relation and prove the whole. Like, but what's the implication of it? Like, what's the good use of it? Before I talk about the good use of it, like, let me just define one small thing. Don't worry, like, it's not going to hurt you. So the essential loop is the closed loop that cannot be contracted or reduced to a single puncture, which means that I don't want something like is not enclosing anything, or something like this, something like a unpunctured monogon that I said. I don't want this. Like something like this is fine. So this is called the essential loop, and bangle is just a copy of them into k parts. You make a k copies of them and arrange them like that, and the bracelet is you are not copying, but you basically go around it and make a self-intersecting curve. So in here, I copied psi 3 times and arranged like them, like so that they will not be intersecting each other. And bracelet 3 is that it's like encircling this area 3 times, but it's just a one curve. And why am I saying that? The reason I'm saying that is that you have to define something more broader compatible sets. And then if you have put the bangles, if you have put the bangles, then we call it C not compatible. If you're adding bracelet, you call it C compatible. And why are we doing that? Because that's the basis. That's the basis of the cluster algebra surfaces. That is conjectured to be basis. Unpunctured case we know. Unpunctured case in 2013, Musiker, Schiffler, Williams have proven that these sets are the basis of the cluster algebra of unpunctured surfaces. So they're both bases. So C not compatible, C compatible, both of them are bases. It's not a union. This one is also basis. The other one is also basis. I just mentioned that. As I already mentioned, punctured case, still open problem. No one knows the answer. But what do we know from the linear algebra? From the linear algebra that we know that if you want to say B or B naught is a basis of the algebra, you have to show that number one, they're subsets. Number two, span. Number three, linear independence. This one is very trivial. But for span, in order to prove the span, you need the result that I mentioned. You need the result to show that the multiplication of any of them actually can be expressed in terms of the variable from the first part, and it's not even a frac or let's say some kind of fractional thing. It's just just the sum of just nice terms. So as you've seen, we proved the span part, and then some of you might have guessed that okay, we're done. No, the problem is that in linear algebra, let's say courses, this one is so trivial and so that no one actually write down the answer, the proof of it. But in this case, this one is the hardest of all. The problem is that in the punctured case, we have no idea why. We have no idea if this is true or no. The reason is that the reason is number one, we know that they are actually subsets of frag A. That's quite trivial. This is quite trivial. But in order to prove they're inside in here, genus zero case is so trivial that no one actually touches. But if the surface contains a genus and a puncture, everything is messed up. There's a very big thing happens in the essential loop that I mentioned. So many people guessing that you need some kind of topological language or maybe even a categorification language, but no one knows. Anyway, so if anyone proved this one, congratulations, you just proved the 12-year-old conjecture. So and then the other future work that we can actually talk about is the generalization of the surface is something called an orbifold. So what is an orbifold? Orbifold is that it's not a puncture. There's an order in the dot in the puncture, which means that there's a group action on it. Sorry, finite group action on the point in the interior, and we call it orbifold. And in the orbifold also there's a triangulation, and in the triangulation of the orbifold we know there's a cluster algebra assigned to there. But one thing that we don't know is number one, we don't know whether the Skein relation holds there. But the bigger problem is that we don't even have a poset language for the orbifold. So if one of you can invent the poset language for the triangulation of the orbifold, that's great. At least sigma for sure. So anyway, so that's I think all I prepared. Thank you so much. Any questions?
Yeah, questions. You can ask slowly.
Yeah, please.
So I have a question.
Mhm.
So is orbifold does orbifold have a high dimension?
It's not about the dimension. It's more maybe in the complex analysis language, you can actually think it as a singularity. Let me just show you real quick. So it's basic example is that if we have a orbifold point in here, it means that and with order, let's say 3, it means that if you swirl around this 3 times, it's the same as this. So in other words, this one has for example, if we have, this is orbifold point, and if we have a triangulation like maybe alpha, beta, gamma, it means that, and with the order k equal 3, it means that the covering space of this is actually rewritten as beta, alpha, alpha, beta, alpha, beta. So, and then so this means that if I actually just go swirl once, just like this, swirl twice, it's like this. Swirl 3, like it's like this. So that's why it's actually just not gonna intersect. That's not gonna have any self-intersection, but just go straight forward. So this is the idea of the orbifold. So orbifold. So of course, more generalization of the orbifold is something called a cone, but no one touches it because that's too general. Like, but anyway, the orbifold. But idea of the orbifold is kind of let's say discussed in the world of cluster algebra because number one, we know the language of this in terms of the snake graph that I mentioned earlier. But other parts we don't know. Number one, we don't know. Like triangulation and all the, let's say, how can we embed this into the cluster algebra? We all know about it, but as I mentioned, the combinatorial tool set in this setup, no one touches it yet. Well, of course, it's because the very last paper about this, which is discussing the snake graph of the orbifold, is published in 2022, so which is really, really new. So that's reasonable, right? Any other question?
I mean, let me ask you maybe very simple, the elementary things. So you had this keyboard mutation.
Yes.
Coming from different triangulations.
Yes.
I was wondering, like, we can think of it as like some kind of operations on directed graph, right?
Oh yeah, exactly.
And now, if I have two directed graphs, can I, like, if I know that I can obtain one from the other by this mutation? Can you say some interesting combinatorial property?
Ooh, wow, never I thought about that. Okay, so number one, if we can embed that directed graph into the triangulation of some kind of surface, then as I mentioned, we know we have a lot of tool. But as I mentioned earlier, like yeah, you can start from quiver itself. It's totally fine, like the Markov quiver or whatever. Like there's a lot of, so you can actually just make in your languages directed graph and assign a cluster algebra. Yes, you can do that. I never thought about it. I don't think there exists a combinatorial toolkit from there to there if I only have a quiver.
And also, if you have a directed graph, can you easily tell whether or not this is coming from certain surface, or is there like some reasonable way to detect whether
I
this
would
is
say there are conditions that you can apply to at least eradicate some cases, for sure, yes, but I'm not so sure whether it is equivalent conditions. I'm not so sure whether it's, let's say, sufficient in this. I don't know. Yeah, but maybe there is, but for that question, I have no idea. I know for sure that there are some conditions that you can say that if you have a quiver, you can eradicate these cases, like something like this, for sure. It's never going to embed it into the surfaces, but in general, I have no clue. But that's a very good point.
okay?
I never thought about that.
What about these mutations? You always had so this is like subdivisions. So you fix boundary, then you add diagonals to add different ways of adding diagonals, and then you have one keeper, right?
Yeah.
What if I start with one triangulation, but then make a subdivision, so maybe refine triangulations, and then I have a refined triangulations.
So sorry, what do you mean by refined
Like
triangulation?
maybe replace one, like just add some more points and subdivide. So essentially it's same surface, but one triangulation could be seen as more refined.
Yes.
triangulation of the other.
Your totally makes sense.
And then you get two quivers.
Yes.
One coming from refined poset. And are they somehow related? Like some containment relations?
I think you're giving me a lot of future questions that I can think about. Which is really nice. I love it. Never thought about it also, but thank you so much. I have to say, yeah, never thought about it. Yeah, but I mean, maybe someone have already done it, but still, good question. And yeah, never thought about it. Yeah. Any other questions or comments or? Okay.
All right. If not, let's take the speaker. Yeah. Yeah. Thanks.